The story of science is filled with grand discoveries. But, it is also a story of quiet moments, of experiments that were almost forgotten. Our journey begins in 1938, long before the world truly understood the power locked inside the atom. At the University of Michigan, a young physicist named Arthur Ruhlig was conducting an experiment. He wasn't trying to change the world or unlock a new energy source. His goal was much more straightforward. He wanted to study the building blocks of matter by firing a beam of particles at a specially prepared target. It was a common type of experiment for its time, a way to peek into the mysterious world of the atomic nucleus. Ruhlig's setup was simple by today's standards. He used a particle accelerator to create a beam of deuterons. A deuteron is a heavy version of a hydrogen atom, with one proton and one neutron in its core. His target was a substance called deuterated phosphoric acid, which means it was rich in these very same deuterium atoms. He was essentially shooting deuterium at more deuterium. His instruments were set up to detect the results of this collision. What he found was something unexpected, a scientific signal that he couldn't quite explain at first, but one that hinted at a powerful reaction taking place right there on his laboratory bench. As Ruhlig analyzed his data, he saw evidence of particles being produced with unusually high energy. He carefully documented his findings, concluding that something remarkable was happening. In his experiment, the initial collisions between deuterons were creating a new, even heavier type of hydrogen atom called tritium. This tritium, with one proton and two neutrons, was then immediately colliding with other deuterium atoms in the target. This secondary collision was the source of the powerful energy burst he had detected. Ruhlig had, completely by accident, witnessed the first ever instance of deuterium-tritium fusion, a process he described in his notes as exceedingly probable. Despite its significance, Ruhlig's discovery faded into obscurity. He published his results in the scientific journal Physical Review, but the world was on the brink of war, and the scientific community's attention was shifting. The concept of fusion was still in its infancy, and its immense potential was not yet widely understood. His paper became a footnote, a small entry in the vast library of scientific knowledge, waiting patiently to be rediscovered. It was a classic case of a brilliant insight arriving just a little too early, before the world was ready to grasp its full meaning and before the tools existed to explore it further. So what exactly did Arthur Ruhlig stumble upon? He had uncovered one of the most promising reactions for harnessing the power of the stars here on Earth, deuterium-tritium fusion, or DT fusion for short. To understand it, let's travel into the atomic realm. Imagine two tiny particles, a deuterium nucleus and a tritium nucleus. As we learned, both are heavy forms of hydrogen. Under the right conditions, extreme heat and pressure, these two particles can overcome their natural tendency to repel each other. They can be forced to merge or fuse into a single, new particle. It is this act of fusion that releases an incredible amount of energy. This process is the universe's most efficient way of creating energy. When deuterium and tritium fuse, they transform into two new things. The first is a helium nucleus, which is a very stable particle. The second is a single high-energy neutron that flies off at great speed. The combined mass of the new helium and the neutron is slightly less than the combined mass of the original deuterium and tritium. That tiny bit of lost mass hasn't vanished. Instead, it has been converted directly into energy, following Einstein's famous equation E equals mc squared. Because the c's in that equation, the speed of light, is such a gigantic number, even a minuscule amount of mass creates a tremendous burst of energy. The reason DT fusion is so special is because it's one of the easiest fusion reactions to start. It requires lower temperatures and pressures compared to other types of fusion, like fusing two deuterium atoms together. Think of it as lighting a fire. Some fuels, like dry tinder, catch fire with just a small spark. Others, like a thick damp log, require a much bigger, hotter flame to get going. DT fusion is like that dry tinder. Its high probability of reacting and the massive energy it releases make it the leading candidate for the first generation of commercial fusion power plants, the kind that could one day power our cities with clean, limitless energy. This is why Ruhlig's accidental discovery was so profound. He had unknowingly opened the door to the very reaction that, decades later, would become the cornerstone of modern fusion research. Scientists today at major facilities like the National Ignition Facility are working to perfect this exact process. They use powerful lasers or strong magnetic fields to create the stellar conditions needed to fuse deuterium and tritium. The goal is to achieve ignition, a self-sustaining reaction that produces more energy than it consumes. It's a monumental challenge, but the blueprint was first sketched out by chance in that Michigan lab in 1938. For more than 80 years, Arthur Ruhlig's experiment remained a hidden piece of scientific history. Its rediscovery began with a clue, a 1986 audio recording of the physicist Emil Konopinski, who had also been a student at the University of Michigan in the 1930s. In the recording, Konopinski mentioned that scientists knew about the high reaction rate of DT fusion even before World War II. This puzzled researchers at Los Alamos National Laboratory. How could that be known so early? Their investigation led them down a rabbit hole of old scientific papers, and eventually they found it, Ruhlig's 1938 publication. It was the missing link, the proof that the power of DT fusion had been glimpsed far earlier than anyone remembered. To verify this lost piece of history, a team of physicists from Los Alamos and Duke University decided to do something extraordinary. They would recreate Ruhlig's experiment. They didn't just want to confirm his findings, they wanted to walk in his footsteps, using modern technology to understand exactly what he had seen. In 2025, they set up their equipment at Duke's Triangle University's nuclear laboratory. Using a modern tandem accelerator, they generated a low-power beam of deuterons, just as Ruhlig had. They even crafted a target of deuterated phosphoric acid, carefully mimicking the conditions of the original 1938 setup. The team's goal was to measure the secondary reactions, the fusion of deuterium and tritium. Ruhlig had inferred this was happening based on the energy of the particles he detected. The modern team, however, had a more direct tool, a sophisticated neutron detector. Since DT fusion releases a high-energy neutron, counting these neutrons would provide undeniable proof that the reaction was taking place. As they ran the experiment, the detector began to click, registering the telltale signature of neutrons produced by DT fusion. History was repeating itself, but this time, every detail was being captured with precision. The results, published in the journal Physical Review C in June 2025, were a stunning confirmation of Ruhlig's work. The team proved that secondary DT fusion does indeed occur under the exact conditions Ruhlig had created. While their precise measurements showed that Ruhlig had overestimated how frequently the reaction happened, his fundamental conclusion was correct. He had been the first to see it. The recreation was more than just a scientific exercise. It was an act of historical restoration. It brought Ruhlig's forgotten breakthrough back into the light, giving him the credit he had deserved all along, and reminding the scientific community that sometimes the past holds the keys to the future. The story of Arthur Ruhlig's experiment is a powerful lesson in how science progresses. Sometimes progress isn't a straight line. It zigs and zags, and occasionally it circles back to rediscover ideas that were ahead of their time. Ruhlig's work was overlooked not because it was wrong, but because the world wasn't ready for it. In 1938, nuclear physics was a young field, and the enormous scale of the energy locked within atoms was just beginning to be understood. The scientific community was focused on fission, the splitting of atoms, which would soon lead to the Manhattan Project and the atomic age. Fusion was a more distant theoretical dream. Today, nearly a century later, that dream is closer than ever to becoming a reality, and it is built upon the foundation of DT fusion. Modern fusion reactors, whether they are tokamaks that use magnetic fields to contain superheated plasma or inertial confinement systems that use lasers to crush fuel pellets, all rely on this specific reaction. The data from Ruhlig's original experiment, and especially the precise measurements from the 2025 recreation, are incredibly valuable. They provide a clearer picture of the physics involved, helping scientists refine their models and design more efficient reactors. It's a direct link from a dusty, forgotten paper to the cutting edge of 21st century energy research. This journey from a forgotten experiment to a cornerstone of modern science inspires us to look at history differently. How many other breakthroughs might be lying dormant in old scientific journals, waiting for the right person to see their potential with fresh eyes? The rediscovery of Ruhlig's work shows that valuable knowledge is never truly lost. It encourages a new generation of scientists to dig into the archives, to question established timelines, and to find inspiration in the work of those who came before them. It reminds us that every experiment, no matter how small or seemingly insignificant at the time, contributes to the grand unfolding story of human discovery. Ultimately, the tale of Arthur Ruhlig is a story of hope. It tells us that the quest for clean, limitless energy is a multi-generational effort, built on the contributions of countless individuals, some famous and some nearly forgotten. The fusion fire that scientists are working so hard to ignite today was first sparked, however briefly, in a university lab all those years ago. As we move closer to a fusion-powered future, we stand on the shoulders of pioneers like Arthur Ruhlig. His story is a testament to the enduring power of curiosity and the beautiful, unpredictable path of scientific progress. A path that can lead us back to the past to find our way forward.